So far we have been focusing mostly on geometry and not really invoking the physics involved. But let's start using some physical situations to understand general relativity. To begin with, we'll work in four-dimensional space, and we know the zeroth dimension will take as time, same as special relativity. Okay, so let's have a construct. Now Einstein concluded that mass curves space-time curvature. I mean, the curvature to space-time is a result of a present mass. Now, space-time curvature will have some geometry, and because of that, there will be geodesics present for this geometry. Let's take a case of some space-time curvature. We don't know how it's produced, but let's assume some spherical space-time curvature. And the geodesics are the great circles. Well, something like this. Okay, now according to equivalence principle, first of all, now we know geodesics actually are straight lines on for a particular geometry. For example, for a two-dimensional geometry, we know geodesic is actually looks like this. For a spherical geometry, we know it looks like a latitude or a longitude, and they are also the shortest. The other way of saying the same thing is that they're the shortest path. Now, if a test particle is left in this curved space-time, is going to follow one of the geodesic. Quantitatively, we can derive this using action principle. We'll talk about that later. But a test particle is going to follow the geodesic. How do we get geodesic is something we are not talking about right now. So when it follows a geodesic, basically it free falls along the geodesic. So if you let a small mass fall from, say, some height onto the surface of the earth, is going to follow geodesic of the space-time curvature formed by the presence of earth, which may not be same as this. Okay, now according to equivalence principle, the two nearby geodesics, let's say you drop two test masses, first here and second here. Now these two test mass particles, when you let them free fall, and these geodesics are very close to each other, according to equivalence principle, 1 and 2 will not have a relative acceleration along the direction of motion, which means all the time they will see each other side by side. One will see 2 on its left or right, and 2 will see 1 on its left or right, vice versa. And this is because of equivalence principle. You cannot differentiate whether it's a free fall or it's non that the gravity is not existing, or in other words, you can say that whether it's accelerating frame or whether it's gravity. So locally, these two geodesics, particles on these two geodesics will not have a relative acceleration if they are following these two geodesics. Now the thing is, how does curvature ends up in picture and comes in picture? Well, because of curvature, as you can see, the latitude start at the North Pole and at the South Pole, but in between they develop separation. So the separation increases and then separation decreases. So in general, you will see that curvature curvature will produce a sideways motion, which means the separation between the two test particles is going to change as it moves along as the two particles move along the curvature. Now this separation is a quantitative measure of the curvature itself. So to understand this, let's say we have two particles and they are moving along two geodesics. Let's say the velocity vector is v. The same guy for certain movement, it moves like this, certain instant of time. Let's say this is p, this is q, and this is p prime, and this is q prime. So if we move from, let's call this w, if we move from p to q, and then q to q prime by simply using parallel transport, or if we move from p to p prime and then p prime to q prime, we end up at the same place. If the two vectors are different, vector 1, vector 2 obtained by parallel transports, then if they are same, then means if 1 equals 2, then there is no curvature. But if there is a difference, then which means curvature is present. And this is a measure of the curvature. And this actually results or actually involves things like Riemann, I'm not sure whether 2n or 1n, Riemann tensor, which I'll probably talk in the following class or next to next class. So this is the idea of curvature. But the main thing of this class was that locally two geodesics, if they have test particles following these geodesics, one particle will not observe the other particle accelerating relative in the direction of motion. They will be both in free fall. We'll make things quantitative in the